I've always loved the idea of being able to see into the sky, to look down and everything be tiny. Looking out of airplane windows always made me feel like I had a whole new perspective. For my senior project, I wanted to take this to a whole new level. I wanted to build something that could go up high, that could show me this new perspective. I chose to launch a high-altitude balloon. This included studying the history, the manufacturing, different scientific concepts, planning, budgeting, studying weather patterns, making sure everything was legal, and then finally launching the balloon and collecting the data. When studying high-altitude balloons, it's important to understand the history and where they come from. High-altitude balloons have become a major informer and scientific necessity. The most common high-altitude balloon is the weather balloon. These balloons help provide information from near space altitudes, but mine didn't get nearly that high. Still, understanding the historical significance can make it clear why such balloons are necessary in our world today. The first known balloons were made out of the intestines and bladders of animals, usually sheep or pigs. These were most commonly used for celebration, particularly by children. One of the earliest documented use of weather balloons was by French meteorologist Léon Tirsac-Debourt. He was actively launching weather balloons as early as 1896. His work was instrumental in discovering the troposphere and the stratosphere. Because Léon Tirsac-Debourt's work was so instrumental, he was honored by having both a crater on the Moon and a crater on Mars named after him. In the early 1900s, a meteorologist and geophysicist by the name of Alfred Wenger used weather balloons to perform experiments which led him to the discovery of his continental drift theory. He published his theory in 1912, and his theory wasn't met with a lot of acceptance. It wasn't accepted until the 1960s, more than 30 years after his death. He's also been honored by having both a crater on the Moon and on Mars named after him. James Van Allen, who would later discover Earth's Van Allen belts, also performed many important weather balloon experiments in the 1950s. This got him recognized as Time magazine's Man of the Year in 1960. Understanding the manufacturing of the balloons, one can begin to see what makes them so special. Due to the process that manufacturers follow, the balloons are durable and light. Both are a necessity for getting to near space altitudes. Weather balloons are typically made of latex, a substance found in many plants. This material acts as a natural preventative for herbivorous insects. It can be extracted from trees similar to maple syrup. It is then molded into the shape of the balloon and cured. Once the balloon has been inflated, it's inspected for leaks and defects before being shipped out. The latex is first poured into temperature-controlled tanks, where stirring mechanisms ensure the latex doesn't settle. The molds are then immersed in tanks of coagulant, mix of water, calcium-based salt, soap, and talc powder, and then heated. The molds are then immersed in a latex tank. The lip of the balloon is formed by rolling the edge with a brush or roller. The molds are then immersed in plain water to remove any excess coagulant. The balloons are then dried and cured, usually being placed in an oven for around an hour. Finally, the balloons are mechanically removed from the mold using a spray of water or air, dried in large tumblers and packaged. There are three major scientific concepts that play out in high-altitude balloons. I would like to go through each of these three using some simple home experiments that we have all seen before and can easily be recreated. Each of the scientific concepts are very important for the successful launch of a high-altitude balloon and to understand how it works. The balloon is able to rise due to being filled with helium. This is a phenomenon we've all experienced with birthday party balloons. This experiment is one that is often done to explain density. A cup is filled with liquids of different densities. In my case, dish soap, oil, water, which has been treated with food coloring. As you can see, the oil is lighter than the dish soap, so it stays on top. I then added water in. Water is denser than oil, and so similar to the helium balloon, the oil rises up. Once the balloon gets up, it begs the question of how does it get back down again? This is due to the lack of pressure pushing on the balloon. In the experiment shown, there is an encasement and a balloon. The bottom of the encasement is flexible. As I pull down on the encasement, the pressure in the container reduces. This causes the balloon to inflate more as the air molecules expand. A very similar concept applies to the high-altitude balloon. As the balloon goes higher in the atmosphere, the pressure reduces. Eventually, the balloon expands so much that it pops. This releases the helium, and the payload comes back down to Earth. Finally, as the payload's coming down, it's important it does not come down too quickly. This is where air resistance comes into play. Objects with a greater surface area have more air pushing up on them, which reduces their speed as they fall. I demonstrate this in an experiment using cupcake wrappers. Some are crunched up, others are partly folded, and others are completely unwrapped. The ones that are completely unfolded fall the slowest. This works very similar to the parachute you'll see me building and testing later. Before I could launch my balloon, there was so much I needed to do. This included everything from understanding money to the weather patterns. I have put on the slide 2 different budgets. The first one is the expected budget. My goal was to do this in under $200. Obviously, I was not successful. This is represented in the second budget seen below. The overwhelming unsuccess of sticking to my budget is mostly due to the fact that my first launch was a complete failure. Something I'll go into a little bit later. I also underestimated the amount of helium that I would need. As helium is a limited resource, it's quite pricey and can be difficult to access. This caused major spending that broke my budget. I also had to determine my flight zone. To do this, I used the Federal Aviation Association, or the FAA's, app for drones and high-altitude balloons. This is called Before You Fly. It clearly lays out legal and illegal airspaces. Here are two pictures that clearly show what the app would represent. It gives longitude and latitude and shows any restricted airspace in the region. Airspace can be restricted for a number of reasons. Hospitals and airports both need landing for their airplanes and helicopters, preservation of wildlife, private property, and other health and safety reasons. I tried to pick a launch site that was over 5 miles away from any restricted airspace. Next, I had to calculate how far the balloon would go. This being my first time, I used an online calculator. I was able to gather information about lift from the manufacturer, and I knew what the size of my payload and balloon were. On the slide, you will see an example of what a larger balloon would look like in this same calculator. In the end, these calculations proved to be rather inaccurate, but they were enough to give me a general picture, which was necessary for legal filing and preparation purposes. I also had to understand the weather. Using global weather tracking websites, I was able to figure out directions of winds at varying heights, including the 30,000 feet I knew my balloon would reach. Based on that, I was able to determine the general direction in which my balloon would fly. These previous calculations of height, distance, and location allowed me to file for a NOTAM, or a Notice to Airmen. This allowed me to inform the Federal Aviation Association about my intended plans for the flight. This then allowed me to easily call air traffic control, tell them my NOTAM number, and get the all clear. Next, I had to create my payload. This included all of the supplies I would use for taking my measurements and collecting data. Originally, I included a camera, but this ended up being too heavy for the final launch. I wanted to be both budget and eco-friendly, so I reused as much as I could. Both the styrofoam box, all of the nails, the adhesive, and the electrical rope were all previously collected from Christmas gifts, trash fashion, and Dad's workshop from all throughout the years. Finally, I had to test all of my supplies. The video I'm about to show you shows me testing the parachute and my video camera. I also had to test my tracker. This was frustrating to say the least, as my class can easily attest to. Though it did result in a much more efficient launch day. After doing these tests, I was able to figure out just how much time to wait after turning on my tracker, and that the camera I had didn't really work, and that I needed to switch batteries, find a new SIM card, etc., etc., which ended up being a good thing to test. Finally came launch day. I showed up to my launch on the first day quite ready, but I immediately encountered some issues. First of all, like I said earlier, I did not have enough helium, which meant I had to go send Holden to get some more. Then I had to call the FAA and ask to delay my launch. This was quite simple. Everyone at the FAA is incredibly nice. Finally, I was able to call air traffic control and get my balloon in the air. I lifted it up and it came back down. I tried one more time. It went up into the air about 7 feet and fell into a tree and popped. Not to be deterred, I tried again. After planning the night before, doing much more research, and finding a clearer area, learning from my mistakes, I was able to call and get a new NOTAM. I was also able to get more helium. And Everything I did the second day was much more efficient. What took me 30 minutes the day before only took me 15 minutes this day. Again, I ended up taking out the camera as it ended up being too much weight, which was fine because the balloon ended up being basically irretrievable. Still, the footage I was able to capture of it going up and the data I received was well worth it. One of the greatest things high-altitude balloons allow us to do is collect data. For me, this was simply looking at travel, speed, and altitude. But high-altitude balloons can be used for so much more. As this was my first time, I wanted to focus on some basics. And I think I was able to achieve a great understanding of my balloon's journey. There's no way to know for sure if the data I got was complete, as I think my tracker may have lost power or gotten too high to send the information back. But the data presented here is what I have to the best of my knowledge. One of the coolest things I was able to gather was a map of my balloon. Each data point is 5 minutes in travel. As you can see, it traveled all the way from above Taos through a great portion of the state. This map has the path easier to see, though the geographical inputs are less clear. This little chunk here at the beginning is actually the setup. So it's more starting at the top and going all the way down. I was also able to use an altimeter to figure out the altitude of my balloon. This came with my tracker. The highest elevation was 31,876.6 feet. This is about airplane level. As you can see in the graph, there was a steady travel upwards until the balloon popped, which led to a plummet in altitude. Finally, we have speed. This, of course, is varied more, based purely on how fast the winds are pushing it and the rate of ascent and descent. The fastest it traveled was when it popped and it went downwards at 100 miles per hour, though it was reaching up to those speeds previous to that. Finally, I would like to thank the following: Mr. Schultz and Mr. Wendland for being my advisors on this project and keeping me focused and making sure everything was produced on time. Mr. Ryan for being the class sponsor and organizing this and making sure it all happens. My parents for providing me with support, both financial and mental, and offering advice that proved to be invaluable. I'd like to thank Mr. Heidenberger for being such a great mentor, providing me with resources, telling me what was worth buying and what really wasn't. Finally, I'd like to thank Karai Gates and Holden Duncan for coming out, filming, and launching with me. I couldn't have gotten the balloon in the air without all of you, so thank you so much. I really enjoyed doing this presentation, and I hope you have enjoyed watching it.